everyone. This is Dr. Ritin Kumar, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology, Mangaluru. Dear students, in the last class, we have discussed regarding the review of vector calculus part 1 of Maxwell's equation. We have discussed the operators such as del operator, divergence operator, curl, gradient, etc. And we have seen the applications of all these operators, and also we have seen the numericals related to these operators. Now, in today's class, we can discuss some of the basic concepts of laws related to the Maxwell equation, that is to the part 2. So first and foremost, let us see the review of Coulombs law. Coulombs law is a quantitative statement about the force between the 2-point charges. When the linear size of the charge bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies may be treated as point charges. All the charged content of the body is assumed to be concentrated at one point in space. Using a torsional balance, actually Coulomb tried to measure the force between the two small charged metallic sphere considered as a point charges, and Coulomb tried to study the variation of this force by varying the magnitude of the charges in pair for fixed distance of separation and by varying the distance of separation for a fixed pair of charges. Based on these studies, Coulomb in 1875 actually he formulated a law known as Coulombs Law. Let us see what is the statement of this law. The electrostatic force between the two charged bodies is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. It acts along the position vector joining the two charges. The force is attractive for like charges and generally it is repulsive for force is attractive for unlike charges and it is repulsive for like charges. So according to the Coulomb's law, the electrostatic force between the charge Q2 due to the charge Q1, between the two charges Q1 and Q2, as we mentioned here, between the charges. So let us keep a charge Q1 and let us keep a charge Q2, and separation between these two charges, let us keep it as R. Okay. In such cases, we can calculate the force as F is directly proportional to Q1 Q2 by R square. Or F is equal to a constant K into Q1 Q2 by R square. Okay. So what is K? K is actually a constant. It depends on the nature of the medium separating the charges. Suppose if the two charges are kept in air, that means intervening medium between the two charges is air medium. In such cases, the value of K can be calculated as 9 into 10 to the power 9. Newton meter square Coulomb to the power minus 2. If suppose the charges are kept in water, in such cases the value of K changes. Okay, depends upon the intervening medium between the two charges. Now let us see regarding the Coulomb's law in terms of vector form. We have discussed here, so we can see that let the position vector for the charges q1 and q2 be r1. I have denoted as r1 and here I have denoted as r2. So the leading vector leading from q1 to q2 can be written as r21 vector, that is equal to r2 minus r1, or similarly q2 to q1 can be written as r12 is equal to r1 minus r2. Okay. So the force existing between the charges F21, that is the electrostatic force between the charge Q2 due to the charge Q1. So what is the force acting on the charge Q2 like this? Because of the charge Q1 can be written as F21, that is equal to 1 by 4 pi epsilon Q1 Q2 divided by R21 square into R12 cap. What is this R12 cap? R12 cap is actually the direction of the force which is acting from the force from the charge 1 to 2. Okay. So next where sigma is the permittivity of the medium, okay, and sigma is epsilon is the permittivity of the medium, and epsilon is equal to epsilon naught into epsilon r. Its value is 8.854 10 to the power minus 12 farad per meter, and epsilon r is relative permittivity, and q1 and q2 are in coulomb, and r is said to be in meter. So continuing with the Coulombs law, as I told, if suppose R21 is a unit vector moving from the charge Q1 to Q2, then the force F21 can be written as 1 by 4 pi epsilon Q1 Q2 by R121 cube into R12 vector. So how to write this? I have denoted there, as I told, I have denoted there here. So it is R12. R12 cap can be written as, so this can be written as, it can be written as R12 vector divided by magnitude of R12. Okay, so this R12 cap can be written as R12 vector divided by magnitude of R12, but we know that the magnitude of R12 is equal to R21. So instead of writing this one as R12, we can write it as R21 also. So R21 square into R21 gives you R21 cube. Okay. So next, so it can be written as 1 by 4 pi epsilon q1 q2 by r2 minus r1 cube minus r2 minus r1. So the unit vector, as I told earlier, can be written as r2 minus r1. So finally, Coulombs law in terms of a vector form can be written as f21 is equal to 1 by 4 pi epsilon q1 q2 by r2 minus r1 cube minus r2 minus r1 vector. So Coulombs law can be written as F is equal to k into q1 q2 by r square. Okay. So Coulombs law, it is actually the electrostatic force between the 2 point charges. Generally, Coulombs law, you can take a note of this one. Coulombs law generally agrees with the Newton's third law. Okay, it is valid for any sign q1 and q2 if q1 and q2 are not same, that is either both positive or negative, then q1 q2 is generally greater than 0, and f21 is now can be denoted as repulsion. So next concept regarding this basics is electric field lines. Electric field lines. What is this electric field lines? An electric field lines is an imaginary line or a curve drawn through the region of empty space so that its tangent at a point is in the direction of the electric field at the point. So the relative closeness of the lines at some places gives an idea about the intensity of electric field at that point. So the concept of electric field lines was developed by Faraday. It is a non-mathematical way of visualizing the electric field around the charged configuration, as we know. So what is electric field? Actually, electric field lines is a path in an electric field, okay, a straight or curved sometimes, such that when you are drawing a tangent, for example, now suppose, see, when you are drawing a tangent, for example, if suppose there is a positive charge and a negative charge, electric field line starts from the positive charge and goes and ends with the negative charge. So when you are drawing a tangent, when you are drawing a tangent like this tangent gives you the direction of the electric field. So what are the characteristics of the electric field? So electric field lines never intersect each other. The field lines are perpendicular to the surface of the charges. The magnitude of charge and the number of field lines both are proportional to each other. The start point of the field lines is at the positive charge and end at the negative charge. As I told, it starts from the positive charge and it ends with the negative charges. So because of this, it forms an open loop as I discussed. So when you calculate the curl del cross E is always equal to 0. Okay. So next one, for the field lines to either start or end at infinity, a single charge must be used. a single charge must be used. Okay, so you can see that on the diagrams I have given. So the electric field lines starts from the positive charge like this, it goes and ends with the negative charge. It forms an open loop. As a result, del cross E is equal to 0. When you are drawing a tangent, this gives the direction of the electric field. Okay, so when there are two positive charges, you can see here two positive charges. So electric field lines are repelling each other. They repel each other like this. They repel each other. When there is an positive and negative charges very near, they form almost a closed curve kind of contour. So this is the direction they go and converges with the negative charges. Okay, so these are some of the characteristic of electric field lines. Next concept to see is electric field intensity or electric field strength. So what is this? It is the electrostatic force F experienced by an unit positive charge Q. So electrostatic fields is experienced by unit positive charge Q. See, for an analogy, see, now let us consider a charge, say for example, let us consider a charge Q1. Okay, like this, Q1. So how to determine the electric field around this one? So how to determine? What we do, let us take one test charge, say Q2. It's a test charge. Test charge is always an infinitesimally small charge, a positive charge, and when you bring this test charge towards this charge Q1, this test charge at a distance r will experience either a force of repulsion or it may experience a force of attraction. It depends on the charge which the source charge is present here. Here Q1 may be positive. If it is positive, our test charge will undergo the force of repulsion because test charge is a positive charge. If Q1 is negative, our test charge will undergo the force of attraction. So Q2 is called as a test charge, whereas Q1 is called as an source charge. So the force experience, so this charge will experience a force. This charge will experience a force that gives you the electric field of Q1. Okay. So it is given by E vector is equal to limit F by Q. Here Q is called as an test charge. So electric field region, you can see that force pulls the positive charges, and you can see that one. So in this diagram, so it is very clear in this diagram. So here this is the negative charge, test charge. So you can see that when it is moved towards the positive charge, this will experience the force of attraction. And here you can see a positive charge, it moves in this direction, it experiences a force of a repulsion. So from which point it experiences a force of attraction or repulsion, till that point the electric field around this charges is going to prevail. So that is an idea of an electric field. Okay, so you can see it starts from the positive and it goes and ends at the negative. So electric field intensity Q2 due to the charge Q1. So how to write? So it is given by E is equal to 1 by 4 pi epsilon Q1 Q2 by R1 square. So we know this one. See, we can write that F, the what is electric field? See, electric field is given by, it is a force experienced by unit positive charge Q2. Force experienced by unit positive charge Q2. So when you apply the Coulombs law, what is E? E is equal to, what is F? 1 by 4 pi epsilon Q1 Q2 by R square is called as F. So you take that Q2 to the denominator, so it becomes E is equal to F by Q. E is equal to F by Q2, that is E, but then what remains? It is 1 by 4 pi epsilon or epsilon Q2 Q1 divided by R square is the expression for electric field intensity or electric field. Generally, electric field is measured in terms of Newton per Coulomb, or alternatingly some people measure it using volt per meter. It can be measured as volt per meter also. So what is the physical significance of electric field? In electrostatic, the concept of electric field is convenient and an elegant way of characterizing the electrical environment of system of charges. So electric field at a point in space surrounding the system of charges present the force a unit positive charge would experience if it is placed at the point. Without disturbing the system, electric field is a characteristic of the system of charges and is independent of test charges at a point to detect the field. And from the knowledge of electric field E at any point, we can readily find the force experienced by the charge Q at the point, and F is equal to, as I told, Q into E. What is Q? Q is uh, the test charge. So electric field is generally a vector. Okay, direction of electric field is the same. So there is no limit of lines drawn in the electric field. Any number of lines can be drawn. So only depends on the relative density of the line in different region of the field. So it is a vector, and direction is same as I told, as drawing a tangent is the direction of the force itself. So it is represented by the gradient of potential along the direction of decreasing potential. It is defined as gradient of potential along the direction of decreasing potential. So let us see a small, what is this electric potential? See, electric potential at any point in an electrostatic field is defined as the work done in unit positive charge from infinity to that point against the electrostatic force of the field. So generally, what is this electric potential? Electric potential, people write it as, actually V is equal, people write it as like this, it is V is equal to W by Q. Okay, and here it is Q2 in our analogy. So what we have did, how to determine the electric field, we brought, say for example, see if there is a charge Q1. So how to determine the electric field of this one? Okay, so what we do, we bring an positive test charge Q2, we bring a positive test charge Q2 from infinity near this Q1. So at a point or at a distance r, this charge will experience a force of repulsion. So if suppose it is an positive charge, positive Q1. Okay, so when it undergoes repulsion, until that region the electric field is present or prevailing. So what is this electric potential? Electric potential means it is a work done by carrying this charge. You are carrying this charge near to the charge Q from infinity to that point against the electrostatic force of the field. So that can be calculated by V is equal to W by Q. So generally electrostatic potential is measured in terms of volt. It is measured in terms of volt, and you know the dimension is m to the 1 L square t to the power minus 3 a to the power minus 1. Electrostatic potential is characteristic of electric field associated with the given charge configuration. So it can be written as, for a single charge, E is equal to minus dV by dx, or E is equal to minus delta V. Okay, so E is equal to minus dou V by dou x Ax cap, dou V by dou y Ay cap, plus dou V by dou Z Az cap in Cartesian coordinate system. And there are some ponders of point regarding the electric field. Electric field, as I told, it's a vector. You know how to determine the direction, just draw a tangent from the line existing from positive to negative charge, it is electric line of force. You draw a tangent, it gives you the direction. So it's a vector quantity and is defined at every point in space, the value of which is dependent only upon the radial distance from Q. Okay, the test charge Q naught itself has the ability to exert an electric field around. Hence, to prevent the influence of the test charge, we must ideally make small as possible. So as I told, how to determine the electric field, you have to bring an test charge unit positive infinitesimally small charge near the source charge. Is it right? So when you bring that one, so whatever the charges you take to determine the electric field, so that charge should be an very small charge, infinitesimally small charge. Otherwise what happens, that effect will come into picture. that effect will come into picture. So that's why when you take a test charge near the source charge, the effect should be very less, but the test charge should experience a force of repulsion or attraction. So this should be taken care. Okay. So next concept to discuss is electric flux. What is this electric flux? So it is the number of lines of forces, it's a number of lines of forces passing normally to the surface. Okay. So lines of forces emanate from the positive charge, as I told, and converges on negative charges. So in the diagram it is very clear, it is a number of lines of forces passing through the surface. So if you are taking this one as lines of forces, so these are the lines of forces, say. So you take a small area like this and calculate how many number of lines of forces passing through this area, gives you the electric flux. So you can see here 3 lines of forces are passing through the electric flux. So you know lines of charges, that means there are positive charges here and there are negative charges here. So positive charges will the number of lines of forces emanate from the positive goes and converges to the negative. In that you take a small area and calculate how many number of lines of forces are passing through that small area, that gives you electric flux. Okay. So flux is generally given by E is equal to EA cos theta, EA cos theta. And what is this theta? Theta is actually, what is this theta? Theta is actually, if this is the normal drawn to the surface of consideration, the angle between the electric line of forces and the normal, this is taken as a theta. This is taken as theta. Okay. So for E is equal to 0, phi is equal to EA cos theta, or that is E is equal to phi is equal to E into A. Okay. And electric flux through the elementary area S is an electric field, can be written as we have written here, phi is equal to EA cos theta, where theta is the angle between the normal drawn to the surface and the electric field. Okay. And regarding the characteristic, it's a scalar quantity and it is generally measured by Newton meter square Coulomb to the power -1. So that is the electric flux. So next concept we can see is electric flux density. So what is this electric flux density or electric displacement? Electric flux density is the flux density passing through the unit area to the direction of the flux. Electric flux density is a measure of strength of electric field generated by electric charge, free electric charge, corresponding to the number of electric lines of force passing through the given area. It represents number of lines of forces passing through given area. So how many number of lines of force? Just like the population density. What is the population density? You take the small area and calculate how many number of people are present in that small area. That gives you the population density. Similarly, how to determine the electric flux density? You take a small area and calculate how many number of lines are passing through that small area, gives you electric flux density. So number of lines, if it is inclined by an angle theta, that is angle between the electric field and the normal drawn. So flux density D is equal to electric flux density or electric displacement D is equal to flux divided by area into cos theta. For theta is equal to 0, you can write like this. For theta is equal to 0, what happens to the cos theta here? We know cos theta that is cos 0, that is equal to 1, cos 0 equal to 1. So you can take flux phi into area A. So next concept to discuss is Faraday's law of electric flux. So it's a very simple law called as Faraday's law of electric flux. What does it tells you? It tells the number of lines of forces emanating from a charge is directly proportional to the quantity of the charge. Number of lines of forces emanating from the charge is directly proportional to the quantity of the charge. So directly proportional to the quantity of the charge. That means, see, if there are two plus say something like plus 2q charges are present, so number of lines of forces emanating will be a particular quantity. Now instead of 2, if I take 3 charges 3q, then more number of lines of forces are developed. So what does it tells you? The number of lines of forces emanating from a charge is directly proportional to the quantity of the charge. Okay, so you can see here, more and more charges will gives you more and more lines, and it also tells you number of lines of forces entering the area is equal to number of lines of forces moving through the area, is also known as electric law, Faraday's law of electric flux. Okay, next, Gauss law. It's a very important law. What is this Gauss law? It's a technique to evaluate the electric field at a point. It's a technique to evaluate the electric field at a point. Okay, evaluate electric intensity at a point due to the symmetric charge distribution. And Gauss quantify Faraday's law of electric flux. Always quantifies the Faraday's law of electric flux. So what is this Gauss law? Statement of Gauss law in electrostatics: the total electric flux over a closed surface, that is taken as you can see closed contour S d dot ds is equal to the total charge enclosed in the surface. So total electric flux, that means what, you take some charges, say something charges say q etc, which is enclosed, q which is enclosed inside a surface. So total lines of forces, that is called as total electric flux through the closed surface is equal to the charge enclosed by the surface. It is obviously the same. If more charges are enclosed in the surface, more lines of forces will come out. If less charges are enclosed in the surface, less lines of forces are going to come out. Okay, so total electric flux is given by a closed integral of d dot ds is equal to the charge. It is equal to the charge. Okay, so like this. So total flux d dot ds is equal to q. So let us prove this one. So now imagine a point charge q kept at a origin of the sphere. So let us take the point charge q. So like this, let us take a point charge q. So something like this, point charge q, which is kept at the origin, say O. Okay, and we can see this one at a radius. So you can see a charge kept at an A and a radius here ds. Let the flux density passing through the small surface area be d. The closed surface of any shape can be imagined to be surrounded by a sphere known as Gaussian sphere. It is surrounded by a sphere known as Gaussian sphere. So the closed surface enclosing the application of Gauss law is known as Gaussian surface. Generally, Gaussian sphere, it doesn't have any shape or size. The charges may be located anywhere within the surface, and Gaussian surface chosen must not pass the discrete charges because electric field is not well defined in the localized of the charges. So Gaussian charge surface means it's a surface drawn the charges enclosed within the sphere. Okay, so what happens now? Total flux leaving the entire surface, see phi is equal to given by flux, total flux is d dot ds. This is the total flux coming out, but according to the flux density, d is equal to q divided by pi of flux through unit area. So our total charge enclosed through unit area, so d is equal to q by pi 4 pi r square, so an. So what you do is you just substitute this one here in this place of d. So we know phi is equal to d dot ds. Okay, so when you substitute the definition of flux density here, so phi is equal to, and this quantity the comes out from the integration, so it is closed integral of d dot ds into an cap. Okay, so next, or that is equal to, but what is this one, this a ds an cap. So ds an cap is nothing but the surface area of the sphere, so our closed surface Gaussian sphere 4 pi r square. So that you just substitute here in the place of this one, and here 4 pi r square gets cancelled out, so the answer will be q. So total flux Q is total flux phi, that is equal to Q. This is called as Gauss law. It's a very important law, and I expect students to completely study this law. So next kind of law we have to deal is differential or point form of Gauss law. So what does this tells you? The divergence of electric displacement density in a medium at a point is equal to charge per unit volume at the same point. So what he tells you that divergence of electric displacement density of at a point. So divergence of electric displacement density del dot D is equal to charge per unit volume, charge enclosed per unit volume at the same point. So that is taken as rho v. This equation is called as Maxwell first equation. So what is the Maxwell first equation? Del dot D is equal to rho v, divergence of electric displacement density in a medium is equal to charge per unit volume. Hope you have understood the Maxwell first equation. Kindly remember that one. Del dot D is equal to rho v. In some textbook they simply designate as a rho. In some textbook they indicate since it is charge per unit volume, so they designate it as rho v. So we can see the next one, very important one, Gauss divergence theorem. So what is this Gauss divergence theorem tells? The integral of the normal component of flux density over any closed surface. The integral, so you can see here the integral of normal flux density d dot ds over the closed surface is equal to volume integral of the divergence of the flux through the space enclosing the surface. That means, see the electric line of forces coming out through the surface in an electric field flux density, it is equal to volume integral of divergence of flux through the space enclosing the surface. So let us prove this one. So what does he tells? Consider a Gaussian surface enclosing the charges with a charge density rho v and electric flux density d. Consider a Gaussian surface enclosing the charges q with a charge density rho v and electric flux density d. Okay, so total charges q is equal to integral of dq. So we consider a charge, see like this, charge q, it is enclosed inside a volume, say like this, it is enclosed inside a volume. So charge q having charge density rho v. So volume in divergence of flux. So he tells that total charge is q, total charge q, that is small charges q1, q2, q3, etc. Integral of delta q, integral of dq, or we know that from law we can write that dq can be written as the volume integral of rho v into dv. Okay, and further, so that is del dot dv is equal to dv, that is from the Maxwell first equation. So we can write it as del dot d into dv. By applying the Gaussian surface, we know q is equal to closed integral of d dot ds. So from equation 1 and 2, so del dot d dv is equal to d dot ds into that is equal to closed integral of v dot d into dv. So this is called as Gauss divergence theorem, and it is a very simple one. Just you have to write two definitions in terms of surface and volume and just equate each other. So this is a very important one, and you have to study this particular Gauss divergence theorem with statement and the proof. Okay, so he is one John Carl Gauss, who actually did this Gauss divergence theorem. So last one in the today's class is Stokes theorem. So only definition and equation is included. What is this one? Curl of a vector over a surface is equal to the line integral of vector along the line enclosing the surface. Curl of a vector over the surface is equal to line integral of the vector along the line enclosing the surface. So here if you see the for magnetic field density intensity H, So closed integral of S del cross H into ds is equal to line integral of H dot dl. So you can see that one in the 3-dimension way. So in the diagram it is seen that though this is the closed surface, curl of this vector is equal to actually the line integral. You can see the line integral of H dot dl. So this law was formulated by Stokes, John Stokes, and the law is and the theorem is called as a Stokes theorem. Okay. So hope you have understood regarding the basics of electric field, Coulombs law, vector rotation, electric flux, and Gauss divergence theorem, and Stokes theorem, Gauss law, etc. So in the next class we can further proceed. So until then, kindly take care. Okay. You can see the hair rising due to the electrostatic in that picture, due to the electrostatic force. Okay, this is an analogy. Thank you.